Hi, let's continue with the calculations for acid and base. In this part itself, we are actually going to look at the formula that you can use to calculate the pH of weak acid and weak base. So to start off, we actually have a weak acid undergoing dissociation, all right? We start off with a concentration of 0.1 mole per dm cube. Let's introduce one term. We can make use of degree of dissociation or ionization, or otherwise termed as alpha, for us to find the concentration of your H plus inside this weak acid, and also thereafter to find the pH. So assuming that alpha is equal to 0.05, then we can use this equation that con H plus divided by concentration of the acid, the initial concentration, all right, to be equal to 0.05, which is actually, it means that about 5%, all right, of the number of the acid molecules that you have will undergo dissociation. So in this case, the calculations will allow us to conclude that your con H plus will be equal to 0.1 times 0.05, okay? And with that, we will be able to also calculate the pH. And I can do that by doing a non-negative log-based stance. So your pH can actually be calculated by doing a negative log-based stance from the value that we calculate here, and you will end up as about 2.3. Okay, so that's the pH of the solution. Okay, the reason why this method is not utilized is primarily because the degree of dissociation varies with the volume and the concentration of your acid. It is not a constant. Okay, so what is the alternative? The alternative is to make use of your equilibrium constant, all right, which will always be a constant value unless your temperature changes. So that will be this will be a far better better method for you to calculate the pH of your weak acid. So Ka itself of Ha, you can actually give a Ka expression as follows here. Of course, in this case, we omit water since water is in excess. Okay, and understanding that if you have say a certain portion of your acid molecules that dissociates, as you can see down here, this pi will then dissociate to break into two equal chunks, which is respectively your H3O plus and your A minus, okay, which are equal. So you probably could imagine that if out of say 100 molecules, 5 of the molecules undergoes dissociation, you get 5 of these and 5 of these. So the key thing is that these two concentrations are the same. And also remember, the concentration of the equilibrium is whatever is left behind, not unlike in this equation where you use the initial concentration. And by actually letting the concentration of the H plus and A minus be X, then we will have Ka equal to X squared divided by 0.1 mole per dm cube, which is your initial concentration. All right, but you need to subtract off by X because this amount of your Ha molecules has already dissociated. So that will be the accurate way for us to go about calculating the pH. To find the pH, obviously, we can solve for X. So at this stage down here, we just need to add to say that there are actually two possibilities for us to work out the numbers. Okay, so let's talk about the method 1. Method 1 obviously will move forward by actually solving the quadratic equations. That means we take everything as quadratic and then we work it out. So you have to solve the quadratic equation. And this will be deemed to be the more accurate method, all right? And you typically will use it when your dissociation is actually pretty high, all right? Which is more than 1%. Okay, based on our numerical analysis, we have found that if Ka is 10 to the power of minus 4 or larger, all right, then you definitely have to use method 1, okay? In method 2 itself, we are going to make an assumption. We are going to assume that the 0.1 mole per dm cube minus X is approximated at 0.1. Meaning to say the equilibrium, the equilibrium concentration of your acid and the initial concentration of the acid is deemed to be more or less the same, which means the dissociation or the ionization is negligible. That means we are assuming X to be really, really small. So obviously by doing that, by making the assumption for method 2, it allows us to simplify our mathematical calculations by saying that it's actually X squared and divide by 0.1, okay? And then with that method, actually, you will be able to make a calculations for your concentration of H plus pretty quickly, because you can now find that your X square will actually be 0.1 mole per dm cube multiplied by Ka, and then you could actually square root this number. Okay. Okay, in the second part, so in a nutshell, what we need to remember is that when you deal with actually weak acid, all right, the approach for the calculations is as such. Remember, and I highlight this, the formula is HA, equilibrium, is to actually make sure that you divide by the equilibrium concentration of the acid, and we could easily pair that equation to this. So that's a formula that you will use for actually a weak acid, all right, to calculate the pH of weak acid. So how about weak base? So for weak base, change to this. So BH plus plus OH minus, all right. So for to calculate the pH of a weak base, we could now take a look at this equation. So from there, correspondingly, we will give a Kb expression, all right, and that will be concentration of BH plus OH minus divided by the concentration of your base, which is at equilibrium as well. And as based on the same explanation, if one of the base molecule decided to ionize, then you'll be producing one BH plus and one OH minus. So these two concentrations will always be equal, all right? Hence, because of that, you will have OH minus square, and there you get the two equations. So in summary, this is the formula that you use for calculations of your pH of your weak acid. This is the formula that you use for the calculations of your weak base. So this is what we term as box 2, all right?